All right, so welcome to deep learning for structured data. So unfortunately, I cannot do this in person this week, but next week I hopefully will see many of you for the next in-person lecture. So we are already in lecture 9, and today we want to talk about architectures for images. All right, so we will see that machine learning architectures for images must respect a unique set of symmetries. And we will start with convolutional neural networks, CNNs, which are very successful deep learning architectures for image data. And then we will look into transformer-based architectures for images, the so-called vision transformer, which now to some extent has replaced CNNs, especially in settings where one has a lot of data. All right, so let's get started. So let's maybe get some high-level intuition for images. So first of all, we can say that images are structured data on regular 2D grids, right? So you can essentially view an image as this regular grid graph, and on each node you have some color information, right? So for example, if you encode colors as RGB values, then this would be a vector with 3 components. And unlike vectors and sets, images have, first of all, local neighborhoods, right? The neighborhoods of these nodes in this graph, and they have also repeated patterns across spatial locations, and they also respect translation symmetries, right? So you can move around the image, but the image, the content of the image still stays the same, right? So you have an image of a cat, you move it around, but it's still an image of a cat, right? And CNNs exploit this local structure via local connectivity and parameter sharing, right? And to formally study images now, we need to define the image space, which is simply the set of all images of a given height and width. All right, so to that, we first have this three integers. All right, so h is the height of the image. W is hence the width of the image, and C is the number of channels that you use to store color information. All right, so hence the image space is simply this set, right? So R, the real numbers, to the power of H times W times C, right? And now we have such an image, X. We can access each individual entry in the set, right? And the first 2 entries correspond to pixels, and the last one to the color channels. Right, so the U here is the height coordinate, the V is the width coordinate, and C denotes the color channel. Right, so hence U, V, and C have to come out of these 3 respective sets. Right, so we can interpret H and W as the height and the width of the image. Right, so it's a very simple way of defining an image. Right, and then to study equivariance properties of architectures for learning on images, we need to introduce the so-called cyclic translation group, right? That basically formalizes how an image is translated. Right, and we define the cyclic translation group as follows. So first of all, we define this set G, and this is a Cartesian product consisting of the set of integers where addition is taken modulo h, and the set of integers where addition is taken modulo w. Right? So again, h and w is the height and the width of the image. right? So now how do we formally define translation? Right, so we have a pair T1 and T2 from G. And now we define the translation action as follows. Right, so we have this tau T that maps an image to an image. Right, and we define this point-wisely or component-wisely, right? So we apply the translation to X. And what we now simply do is we take the height coordinate U and simply subtract T1. And we do the same for the width coordinate V. So we subtract T2. Right, and the color information, the information, the channel stays exactly the same. Right, and the indices here are taking modulo H and W. Right, so we have to ensure that this subtraction stays within the height and the width of the image. Right? And now we want to define CNNs. And in order to understand CNNs, we need to introduce the central operation of convolution. And I believe many of you already understand the intuition or even the formal definition of convolution. But let's repeat this here anyway. So intuitively, as you might know, we slide a frame or a window of a given height and width from left to right over the image. And then we compute a value for the top left element in the frame. Often in textbooks, one takes the center element, but in modern deep learning architecture, it's usually the top left element. But it doesn't really matter. It's essentially the same operation. Right? Okay, so how is this convolution or this discrete convolution defined? So as input, you have an image, height is H, width is W, number of channels is Cn. And then you have a so-called kernel, which is an element from this set. Right? So you have a height, a width, input channels, and output channels. Right? And the application of the convolution essentially maps an image to another image of the same height and width, so H and W, and only the number of color channels changes to C out. Right? And now the question is, how is this defined? Right? And this is essentially defined here in this long formula. But what we essentially do here is just a simple dot product. So maybe let me explain this with an illustration. Right? So we have our image. Height and width is H and W. And now what we do is, right, so we start with here the first top left element. And now we have this frame or window of height KH and width KW, right, our kernel. And now we look at essentially each of the pixels and their color information in this frame or in this window and multiply it with the corresponding value in the kernel. Right? So this is essentially formalized here. Right? So the first two sums here simply explore every pixel in this frame here or in this window. And then we multiply it with the corresponding value in the kernel. Right? And we do this for every channel from 1 to Cin. Right? And we do this operation for every channel from 1 to C out. Right? And then we just add a bias here. Right? So what we essentially do is we do a dot product. Right? So we can also view this as, well, we take these the square here, we flatten into a vector, we flatten the kernel into a vector, and then we just do a standard dot product in the Euclidean space. Now that's another way of viewing this. right? And we essentially do this operation for every coordinate. And then, right, so we do this operation, we compute this value, and then we write it into the top left corner of the frame, right? So then the next one would be, let's change the color here, would be then this frame here, right? And then this one here, and so on. Right? So you look at these overlapping frames. And then in the next row, you would do something like, sorry, that's not correct. So we'd consider this one, and then this one, and so on. Right? And by this, you map the original image to another image of the same height and width. Right? And this is maybe illustrated here. Right? And what is specifically illustrated here is the modulo height, the height and the width. Right? So for example, you consider this coordinate, and now you want to apply the kernel, right? So this is a 3x3 kernel, right? So it obviously goes outside of the range of the image. So you have to apply your modulo operation, right? So you have, first of all, these kernel values, right? And they end up here. Then you have these kernel values, right? So this one gets mapped here. This one gets mapped here. And then this area ends up here. Right? That's how you do the modulo. Right, and now we have to examine the equivariance of convolutions under the translation operation. Right, and we essentially want to show the following theorem. So we have an arbitrary translation from our cyclic translation group. We have some arbitrary image, an image from our image space. And now we want to show that first translating the image and then doing the convolution with a given kernel is the same as first doing the convolution and then applying the kernel. Right? And this is actually not very hard to prove. You essentially just apply the definitions. Right? So we do this, we show this for each coordinate. Right? So we start from the left. Right? So we first apply our translation to our image data, and then we apply the convolution. Then we look at our coordinate, UV Cout. Right, and this is just defined here, right? So this is just the definition of convolution as we have defined it 2 slides ago. Right, right. So we apply the convolution to the translated image. Right, this is really just applying the definition. Right, and then in the next row, we simply write out the translation explicitly. Right, so we take our coordinate u plus a, and we subtract t minus 1, and we do the same for v plus b, and we subtract t2. Right, and the channel information stays the same. Right, and hence this is the same as applying the convolution to the original image x, and then looking at the translated coordinates. Right, and this is just the same as applying the convolution and then the translation with regard to the original inputs. Right, so here, right, if we go from here to here, we have just translated the coordinates. Hence, equality holds pointwise. All right, and convolutions are typically combined with nonlinearities. Hence, we also have to study the equivariance properties with regard to translation. Right, so we have some arbitrary nonlinearity, for example, Irelu function, sigma, and then, as before, we apply these nonlinearities component wisely or point wisely. This is just defined here. Right, and then for all translations T in our cyclic translation group, it holds that we can first apply the translation to the image and then apply the nonlinearity, or we can first apply the nonlinearity and then apply the translation. It doesn't matter. Right? And the intuition is simply because we don't change the information in the color channels. Right? And we can also quickly prove this. This is even easier. Right? This is somewhat immediate from the pointwise application. Right? So we apply the translation to X, and then we apply the nonlinearity pointwisely. Right? This is just done here. This is right. So this is just the application of this this definition. Right, and then we explicitly write out the translation, right? So we subtract T1 and T2 from U and V respectively. Color information does not change, and hence this is just equal to first applying the nonlinearity and then the translation, right? And this gives with regard to the coordinate UVC, right? And hence we have shown the equivalence of the two. Right, and hence we can easily now prove the following result. So any composition of circular convolutions and pointwise nonlinearities is translation equivariant. Right, so this is now just an application of the previous theorem that the convolution operation is equivariant, and that pointwise applications of nonlinearities is also translation equivariant. Right, so by the previous theorem and the previous proposition, each layer is equivariant. And as we know, the composition of equivariant maps is equivariant. Right? I think you proved this in one of the exercises. Otherwise, it's a very, very easy proof where you basically just apply the definitions of equivariance. Okay, so now we know the convolution operation, and now we want to look at the basic CNN architecture. Right, and to that, we first define a CNN block and batch norm. Right, so a standard CNN block is defined as follows. So you have an image and you map it to the following. So first of all, you apply convolution to the image, and then you apply a so-called batch norm and then a nonlinearity. Right, and again, the nonlinearity is applied in a pointwise fashion. Right, and here Bn, as I already said, denotes a batch norm, and let us quickly understand batch norm. Right, so we already know layer norm. We have defined this when we introduced transformers, and batch norm is essentially the same as layer norm. We just apply it in a batch-wise fashion. Right, and usually convolutions are trained in mini batches. Right, so the input to a CNN architecture is a tensor defined as follows. So we have images of height and width H and W, and C is the number of channels, and we have B many images in each batch, and hence we get this tensor. And so capital B is the batch size. Right, and then batch normalization is applied per channel. Right, so we essentially do the same operation as with layer norm. Right, so first of all, for each channel C, we compute the mean. Right, so we sum up all the entries in a given batch, and then we divide by B times H times W to compute the mean. Right, and then again, as with layer norm, we compute the sigma squared for each channel C. Right, so we take the original entry, we subtract the mean for the given channel we have just computed, square this, sum this up, and then divide by the total number of entries. Right, and then to define batch norm, we just subtract the mean and essentially divide by the standard deviation, where C is where epsilon is some small value for a numerical stability. Right, and then as with layer norm, we scale by the scalar and add this bias term. Right, just basically just layer norm, but applied in a batch-wise fashion. Right, and in practice, the mean and the sigma squared are computed from the current mini batch during training, as we have defined, and then during inference or test time, we use running averages. Right, and in place of batch norm, one can of course also use a layer norm, or we can entirely omit the normalization. Right, this is just a design choice and depends on the data that you have. Okay, right, so now we understand the basic CNN architecture. We want to look at a architecture that works specifically well in practice. Right, and the CNN architecture we have just defined is an architecture that essentially maps an image to a vector, and then you can do a single classification for the whole image. So image classification. But many computer vision tasks are actually dense prediction tasks. Right? So the model should output a prediction for each pixel, so for each spatial location. Right? So a semantic segmentation class for every pixel. Right? So, for example, if you have an image of, let's say, I don't know, some cat, and you also have some weird tree, and you might also have the sun in the picture, and the rest is background. So you would have 4 classes, right? And then, for example, if you have given, let's say, this picture, you should predict class label cat. And if you have this pixel here, you should predict tree. And if you have this one, sun, and if you have a pixel like so, it should output a background. Right? So hence, as input, you have given your image. And as output, you want a probability for each pixel and each class. Right? So if you have the pixel UV and class K, then this is the logit for the class K at pixel UV. Right? And the final predicted label is simply the argmax over these K classes. Right? You just simply compute the argmax over these K values. And this is your given predicted class. Okay, so now the question is, well, how do we do this segmentation task? How do we define a segmentation model? And a very successful architectures for segmentation is UNet. And UNet is a so-called encoder-decoder architecture that uses CNN layers with skip connections. And the basic idea is that the encoder repeatedly reduces the spatial resolution. So it essentially reduces the height and the width of the image while increasing the number of channels. And then the decoder essentially restores the spatial resolution, and at each scale also uses the original downscaled image of each step to upscale the image. Right, so these, and the original image is inserted into the upscaling layer with skip connections. So you preserve the fine localization information that would otherwise be lost in this during this downscaling to this bottleneck. Right, so to draw a schematic picture, it would look like this. So you have your original input, your original image, height and width is H and W respectively. Then you do a first downsampling. So you have the height and the width of the image. You do this a multiple time, and then you arrive at this bottleneck. And then you upscale again. Right, so you go from a image of size H divided by 4 times width divided by 4 to an image that has height h divided by 2 and width w divided by 2, right? Until you arrive at the original image size. Right? And now we have to understand how we actually do this downsampling and this upsampling in practice, how we can actually implement this. And this is actually very simple, right? So let's first study downsampling. All right, so we have an image of height h and width w, and we assume that h and width are divisible by 2. Right, so we somehow want to define a function that takes as input an image and maps it to an image where the height and the width is halved. Right, and one way of doing this is by 2 times 2 max pooling. Right, and for each coordinate, this is defined like so. This looks a little bit complicated, but it's actually very simple. So we have an image of height and width h and w. And now you essentially divide the image into blocks of size 2 times 2. Right? So each block has exactly 4 entries and so on. All right, so 4 entries here. Right, and now for each block, you simply apply a max operation. Right, and you get a value, the maximum, and then you essentially replace each of this block with a value, with a max value. Right, so you essentially reduce 4 points to 1 point. Right, and hence you have the height and the width by 2. Right, so each non-overlapping 2 times 2 spatial block is replaced by 1 value per channel. Right, you do this operation channel-wise. Right, and the upsampling is even simpler. Right, so you have an image of this height and width, h and w, and you essentially want a function of this signature. So the input is the image of height and width h and w, and you essentially want to double the height and width of the image. Right, and one simple way of doing this is nearest neighbor upsampling. And the idea is very simple, right? So you have your image. And now you essentially look at each pixel, right? So for example, take the first one here, and you simply make 4 copies of this pixel, right? So you place each pixel by a block of size 2 times 2. Right, so each value is copied into a 2 times 2 spatial block. All right, so very simple. All right, so now let's formally define a UNet. So BL and CL are CNN blocks. All right, so this L denotes the layer number of the encoder and the decoder layer. Right, and as we know, the down now reduces the spatial grid, halves the image, the height and the width of the image, and up increases it again. And then we also have this cat operation that concatenates tensors along the channel dimension. Right, so how can we formally define this? All right, so we define an L level UNet that first of all, we have our input, our image. We apply our first CNN layer. All right, so this is the first CNN layer. We get some output, and then we do our first downsampling operation. So we have the height and the width of the image, and then we apply our convolution, right? And we do this for L layers. Right, and then we have the derived at the bottleneck representation, and then we upsample again. All right, so this is the output of the Lth encoder block, encoder layer. Right, let's say this is DL. So then we simply apply an upscaling layer to DL, and then we concatenate this with the output of the L-1th encoding layer. Right? Otherwise, too much information would have been lost in this downscaling. Right? And then usually the logits are typically produced by a 1x1 convolution. So the height and the width of the kernel is simply 1. Right? And as output, you get a tensor of shape h times w times k, where k, the capital K, is the number of classes. Right? And hence you can do a classification for each pixel. Right, and this concludes this short introduction to CNNs. And if you want to have more background on CNNs and their use in vision, you can, for example, check out this book by Goodfellow, Benjou, and Corville. And yeah, historically, CNNs trace back to the so-called neocognitron, which was defined already in the 80s by a Japanese researcher. And then again, it was popularized by LeCun, and LeCun really got it to work in practice. Right, and then a couple of years later, there was this so-called ImageNet area where deep learning became very successful. Right, so there was this famous paper by Krzyzewski et al., supervised by Hinton, that really showed that if you train CNNs with a lot of data, it works very well. Right? And for example, also the ResNet architecture using these skip connections was introduced in 2016. Right, and then batch normalization was introduced by this paper by Ihoffe and Segedi in 2015. All right, so now we want to leave CNNs and look at more modern architectures. Right, so CNNs were successful 10 years ago. I mean, they're still widely applied in industry and also in research, but they're more and more replaced by transformer-based models, which leads us to the so-called vision transformer. Right, so we know that CNNs impose strong locality and also employ a translation equivariant inductive bias. And the vision transformer, VIT, instead treats an image as simply a sequence of patch tokens and then applies self-attention. So what does that mean? Right, so you have an image, and now you simply divide the image into these patches of height and width p, right? Non-overlapping patches, like so. Right, and now you take each of these patches, p times p, flatten it to a vector. Right, so this is then a vector of p squared many entries. Then you apply some transformation to this vector, to each of these vectors for each patch. So you map it to some higher dimensional space, and then you simply concatenate the outcomes row-wisely. And this is then simply the input to your transformer. Right? And this is essentially already the idea of the vision transformer. So it's very simple, but it works very well in practice. Right? And the motivation is as follows. So first of all, you have this global receptive field from the first layer. So each token can attend all others. Right? And in the CNN, you only have this local aggregation. Right? And what's also important is that now you have this uniform architecture across different data modalities, right? So we already know that we can very successfully apply the transformer for text data. With the VIT transformer, we can also, with the vision transformer, we can also apply it now to image data, and we can also apply it to audio data. We will later see that we can also apply it to graph data, right? So you essentially just have to optimize your hardware infrastructure to a single uniform architecture, right? And of course, this is very good. And then the transformer and also the vision transformer has excellent scalability with data and model size, right? So it works very well on modern GPU hardware. And as you increase the amount of data, they usually perform better. Right, and compared to CNNs, VITs have a weaker built-in spatial inductive bias. And typically, in order to get them to work, you need more data and more engineering, for example, some data augmentation to increase the amount of training data. Right, and let's formalize this idea I've just explained. Right, so we somehow need to understand how to convert images to tokens. So we have as input our image, and we assume that the height and the width is divisible by the patch size p, so the height and the width of this patch. And now we simply define this n, which is just h times w divided by p squared. And hence, this is the number of patches. Right? So you take your image and you divide it in non-overlapping patches of height and width p. And hence, you get n many patches. Right? This is a simple calculation. And then in addition, each patch covers an area of p squared. And hence, one needs a vector with dp many entries, where dp is simply p squared times the number of color channels. Right, so you have, well, okay, this is very easy. You have height p, width p, so this is area p squared, and then you have c channels. Right, so this is dp. And this is the number of components you need to store this flattened patch. Right, this is just an artifact here. All right, so we can define this patchification operator, which simply extracts non-overlapping patches from an image. All right, so we define this patchification operator that as input takes an image and maps this image to a matrix with n rows and dp many columns. Right, so it simply extracts non-overlapping p times p patches, flattens each of them to dp, and stacks them as rows. Right, and this is essentially then used for the patch embedding. Right, so the patch embedding simply takes these flattened patches and maps them to some higher dimensional space. This can, for example, be done with a simple linear transform, but you could also, for example, use something more expressive, for example, a feed-forward neural network. Right, so we just define this here with a linear transformation or an affine transformation. Right, so you have your flattened patches here, and then you simply apply a linear mapping and a shift by a bias. Right, so an affine transformation. All right, nothing complicated. All right, so we can also illustrate this. All right, so we have our image, height h, width w. We have our patch height and width. We divide our image in these patches. Right, and then we essentially flatten each of these patches into a vector. Then we apply some transformation into some higher dimensional space. And then we simply stack the resulting vectors into a matrix in a row-wise fashion. right? And then this is simply the input to our transformer, right? And this already leads us to the definition of a WIT block, right? And essentially, this is just applying a standard transformer architecture with multi-head attention to this matrix we have just defined, right? So assume this is the matrix of these flattened and transformed patches. So we have n times d, and we just apply our standard multi-head transformers. We apply layer norm to H, multi-head attention. We have a residual connection. We again apply layer norm. We apply feed-forward neural network, and we have a residual connection. And as always, the feed-forward neural network is applied in a row-wise fashion. Right? So then this is one WIT block or one WIT layer. And then you can essentially compose several of those WIT layers to get a WIT architecture. Right, and this WIT transformer was defined in a paper with a funny name. An image is worth 16 times 16 words. And it was published in this paper by Tuzowitzki, and also the second author was Luca Bayer, who actually did his PhD in Aachen, I believe, with Bastian Leibe. Right, and nowadays there exist many variations of this WIT transformer, for example, Dino and so on. But if you understand this WIT transformer, then it's very easy to follow all of these papers. Right, and this concludes this lecture. And I hope I see many of you in person next week. Thanks a lot.